Hello everyone, and welcome. Today, we are going to explore a powerful technique known as morphological region filling. At its core, this is a method from digital image processing that allows us to intelligently fill internal holes within binary images. We'll be looking at how this is achieved using iterative operations, a fundamental concept with major applications in computer vision. So, what is the specific challenge we're addressing? The problem, as you see on the left, is that binary images, simple black and white images, often have internal holes or gaps. These gaps aren't just a visual issue. They can seriously interfere with computer vision tasks like object analysis, measurement, or recognition. While you could try to fill these pixel by pixel, that's inefficient and often unreliable. We need a more systematic and robust solution. The diagram on the right gives us a perfect high-level preview of that solution. We start with our original image, which has clear holes. Next, we define a seed point, a single pixel we place inside the hole, and a mask, which is the boundary of our original object. Then comes the core of the process, iterative dilation and intersection. This simply means we grow our seed point outwards, but the mask, our boundary, stops it from leaking outside the object. We repeat this grow and constrain process. The result, as you see, is a completely filled image, with no internal holes. This slide defines our problem and gives us a visual roadmap for the elegant, morphological solution we're about to explore. To understand that grow and constrain idea, we need to know three basic morphological operations. These are the building blocks of our algorithm. First, dilation. You can think of this as expanding or growing an object. It adds pixels to the object's boundaries. Next, erosion. This is the exact opposite. It shrinks an object by stripping pixels away from its edges. And finally, intersection. This is a logical operation. It looks at two images and creates a new image containing only the pixels that overlap in both. For our hole filling task, we will primarily use dilation to grow the seed and intersection to constrain it. This flowchart shows the logic of the algorithm in action. It's a continuous loop. We initialize our seed, then, we dilate the seed region to make it grow. Immediately after, we intersect it with our boundary mask to make sure it hasn't grown too far. Then we check for convergence. This is a simple question. Did the image change in this last loop? If yes, we repeat the process, dilate, intersect, check. If no, it means our growing region has completely filled the hole and can't grow anymore. The process is complete. This entire process can be described with one elegant mathematical formula. Here, xk is the result of our current iteration. It's calculated by taking xk minus 1, the result from the previous step, and dilating it with a structuring element, b. That result is then intersected with ac, which is the complement of our original image, or, more simply, everything except the original object's boundary. We just repeat this formula, feeding the result of one iteration back into the next, until the image stops changing, until xk is identical to xk minus 1. Let's visualize that equation. At iteration 0, we begin with our single seed pixel. In the first few iterations, you can see the region rapidly expanding outward from that seed. This is the dilation part of the formula. Finally, the growing region hits the internal boundaries of the hole. The intersection part of the formula stops it from going any further. This is convergence. The hole is now perfectly filled. For our demonstration, we've chosen a real-world example. This Batman logo, which is damaged with numerous internal holes. It's the perfect test case to see if our algorithm can fill these complex gaps correctly. Our code approach, using Python, follows 5 key steps: load and binarize the image, identify a seed point, create a structuring element, iterate the dilation and intersection, and finally, visualize the results. Here's the first part of our code. We import the libraries, load the image, and convert it to binary. This implementation cleverly uses a flood fill operation to fill the shape, followed by a morphological closing to clean up any small remaining gaps. This second block of code is purely for visualization. It sets up a 3-part plot to show our original image, the final filled image, and an overlay highlighting the changes. And here are the final results. On the left, the original image with holes. In the middle, the filled image, which is now a solid, clean logo. And on the right, the red overlay confirms exactly which areas our algorithm successfully identified and filled. The process was a complete success. And that is the power of morphological filling. We've taken a complex problem, holes in an image, and solved it with a simple, iterative algorithm, as demonstrated with our code. This turns a flawed image into a complete, analyzable one. Thank you.